The Diffie-Hellman Key Exchange protocol enables two parties, Alice and Bob, to securely establish a shared secret key over an insecure channel. This shared key can then be used for encrypting and decrypting messages. In a previous video, we found that certain numbers, called generators, can generate all values in the set z star sub p through repeated multiplication. Z star sub p represents the set of all non-zero integers modulo p. These numbers are essential for this key exchange process, and it's highly recommended that you watch that video before continuing on with this one. In this video, we'll explore the Diffie-Hellman protocol step by step, demonstrating how Alice and Bob can effectively generate their shared secret key using chosen generators. I'll begin this video off by going through the steps on how to produce this shared secret key, and then we'll look at an example involving the numbers we found in that previous video. So let's just run through the steps very quickly. In the first step, Alice and Bob must agree on two public parameters, namely a sufficiently large prime number p and a generator of that set, which we'll call alpha. The next step is for Alice to choose a secret number a that's in the set z star sub p, and a will always be between 0 and p. Using this secret number and the two public parameters alpha and p that were agreed upon, Alice goes ahead and calculates the value of capital A, and this will be made public. So we have capital A being made public and lowercase a being kept secret by Alice. Now similarly, the same process occurs with Bob, where Bob chooses another secret number, B, that's also within that set, and it is also greater than 0 and less than P. Bob will compute and publish his own value of capital B using that formula. B is equal to alpha raised to the power of B mod P. In step 6, Alice and Bob exchange their public keys capital A and capital B. Now using Bob's published value of B, Alice computes the shared secret S. We have S is equal to Bob's value of B raised to the power of A. That's the same thing as the second line of this equation, except that we've replaced B with what it actually is, the formula itself, and using some basic exponent laws, that results into the following equation, alpha raised to the power of B times A mod P. Now at Bob's end, the same thing happens. Bob takes the value that Alice has published, capital A, and raises it to his secret, lowercase b. After all is said and done, you'll notice that the equation in which Bob uses to calculate the shared secret value is the same as Alice's. So the value of S must be the same amongst the two. And finally, once S is established, Alice and Bob can use it as the key for a private key system, such as the Data Encryption Standard, or DES. So let's go ahead and do an example. In that previous video, we learned that the generators of Z star sub 7, and remember, the generators are represented by the letter alpha, were 3 and 5. Alice and Bob will agree on one of these values. Let's say they agree on the value 3. So we have our alpha value of 3, and we have our p value of 7. Looking at step number 2, Alice will now choose a value of a. So a can be anything from 1 to 6. Let's say she chooses the value of 4. So a is equal to 4. And again, this is a secret in which she will keep. Now using this value and everything else, we'll move on to step number 3. We'll say that capital A is equal to our alpha generator of 3 raised to the power of 4 mod 7. 3 to the power of 4 is 81 mod 7, and we need to compute this. We're looking for the remainder when these two numbers are divided. I'll use a modulus calculator that's found on our website. I'll type in 81 and mod 7. We end up getting a value of 4. So A is equal to 4. And this will be published. Now moving on to step number 4, we'll repeat this process but with Bob calculating his value of capital B. Now he must start by choosing a secret number B. It can obviously be the same as Alice's, but for the sake of showing something different, let's say that Bob chooses the value of 5, just as long as it's greater than 0 and less than P. We'll next calculate capital B by taking the alpha, which we chose to be 3, raise it to the power of 5, mod 7. Okay, 3 to the power of 5 happens to be 243 mod 7, and we'll use our modulus calculator to find out what that is. 243 mod 7 gives a value of 5. Once capital A and capital B have been published, both Bob and Alice can go ahead and compute their shared secret. So we'll begin with Alice computing her shared secret. We have S is equal to what we found for B raised to the power of A. That was Alice's secret number. And again, that lowercase a value is 4. And we'll take this to mod 7. So 5 to the power of 4 happens to be 625. And using our modulus calculator, 625 mod 7 makes 2. Now we're expecting this to be the exact same for Bob. Let's calculate Bob's shared secret. We'll take Alice's published value of capital A, and that was 4. We'll raise it to Bob's secret value of B. Lowercase b happened to be 5. Mod 7. 4 to the power of 5 is 1024. Using our modulus calculator one last time gives us a value of 2, and it is clear that they are exactly the same. Now notice that both Bob and Alice have established the same shared secret S without knowing each other's secret values lowercase a and b respectively. Despite much research, recreating the shared secret S from the public values capital A, capital B, the generator, and the prime number p without knowing lowercase a and b remains a hard problem in mathematics when p is sufficiently large. Now for us, when we chose a value of p being 7, that is very small. For simplicity's sake, we chose a very small value of p. Nevertheless, this form of reverse engineering is known as the discrete logarithm problem. For example, suppose we know p to be 541 and the selected generator to be 13. If we look up Alice's public key, which happens to be 429, we would need to solve this equation to figure out Alice's secret, lowercase a. Or, in other words, this problem, where 13 raised to the power of a is congruent to 429 mod 541. Both expressions here indicate that when 13 raised to the power of a is divided by 541, the remainder is 429. And one approach to solving for it, if we were to reverse engineer and find out what that secret is, would be to calculate every power of 13 from 1 to 540 mod 541 until we find a remainder of 429, which is extremely slow and impractical, especially when the value of p is very large for both humans and computers. Now, if you like this content, I'll be producing another video where I show you what would happen if an eavesdropper Eve had access to capital A and capital B, but not lowercase a or b. In other words, we'll be going through a man-in-the-middle attack on the DH key exchange. Thank you so much for watching. I hope you learned something new.